we know that there's a magnetic field around a current carrying wire, and we've looked at the direction of that, or the shape of that. So if this is my wire and the current's flowing this way, we know that the current, or the magnetic field, comes out over here and goes in over here. If we were to look at a top-down view of this, so here's the wire, and current's coming up out of the page at me, then there is a magnetic field line that is a closed loop, like all magnetic field lines are, that is concentric with that wire. And there's another one out here, and there's another one out here. And as we get farther and farther and farther from that wire, the magnetic field strength gets smaller and smaller and smaller. And so, yes, they're all in the same direction. We're all going counterclockwise here. But how strong is this magnetic field? Well, it turns out that the magnetic field strength is given by this equation. B is equal to mu naught times I over 2 pi r, where mu naught is the permeability of free space. It has this unit, or value, I guess, 4 pi times 10 to the negative 7th Tesla meters per amp. And then r is the distance in meters from the wire to wherever you're measuring this. So if r is fairly small, then your field strength is fairly large. But the further you get this distance from your wire, if this is r, then of course the field strength is less and field strength is less. It's an inverse law. It's not an inverse square law. It's not quite like the charge or the field around a magnetic, or sorry, around a charge, but it is an inverse law. The further you are from that wire, the weaker the magnetic field. However, if we increase the current through the wire, we're going to make the magnetic field stronger. Now, this is kind of a cool problem because we can actually figure out how much force there are between parallel wires. You're like, well, why would this be a concern at all? Well, we use wires all over the planet to move current from one place, to move power from one place to another. Now, we do that at low current and high voltage, but there's lots of times where parallel wires are carrying current next to each other. And there's a couple things I want to investigate, but if you think about it, what we have here is current moving through this wire. And so we're going to look at the magnetic field generated by this wire. And that magnetic field is out of the page over here. Out of the page over here. And of course it would be into the page on this side. Right? And so that means that this magnetic field is perpendicular to the current in the wire. And that of course means that there is a force on that wire. And so there is a force between two current conducting wires that's either going to act to pull them together or push them apart. And so what we look at is the magnetic field produced by one wire, and that of course is equal to this. And that magnetic field is going to exert a force on the current in this other wire. And remember, the force acting on that is equal to ILB sine theta. F equals ILB sine theta. Okay, so here's what we have. We have this, which is B, and then D is the distance between them. And then we have IL, and as long as they're parallel to each other, then the sine of 90 is 1, and we don't have to worry about it. And so, or the wires are parallel to each other, so the current's perpendicular to the field, right? So we combine those two equations together, and we get this one. So, right, this is B, and this is the current in the other wire and the length of the wire in the field. Now, which way are these forces going to act? And actually, that's not all that hard of a question to answer. So this current is up, and so that means if I put my thumb, so it's pointing up, and wrap my fingers, that means on the left side of this wire, the magnetic field is out of the page. Now, what the question is what does, and over on this side it would be into the page, which way is the force on that wire? Well, so I point my fingers in the direction of the current, so I point my fingers up, and then I curl them in the direction of the magnetic field, which means out of the page, so they have to come towards me. In order to do that, my thumb has to point right. So the force on this wire is this way. And by a very similar argument, we can find that the force on this wire is this way. So the force between two parallel wires when the current is in the same direction is together. However, if they're in opposite directions, well, what are we going to see? Well, So again, we'll look at the magnetic field. Let's look at the magnetic field produced by this wire. Over here, it's into the page. Right, we put our thumb up, and then our right hand points, curls in the direction of the current, or in the magnetic field, so it's coming out on the left side, but in on the right side, so it's coming out over here, right? What's going on over here? Well, I point my fingers in the direction of the current, which is down, and then I curl my fingers in the direction of the magnetic field. So first I pointed my fingers down, but then I have to curl them into the page, and in order to do that, my thumb has to be pushing to the right. So this force is this way. Now what about the force on this one? Well, if we look at the magnetic field generated by that second wire, I'll use green for that, then the magnetic field from this wire over here is, let's see, that is going that way, and so it is into the page over here. Into the page over here, sorry. And so then I point my fingers in the direction of current, curl my fingers in the direction of the magnetic field, and we see that the force is this way. And so this is apart. So it's when the two parallel wires are carrying anti-parallel currents, then the wires want to move apart. If they're carrying currents in the same direction, then they're going to want to move together. Now, we can stack a whole bunch of parallel wires next to each other, and when we do that, we get a solenoid. Okay, so that's not quite true. The solenoid is a long coil of wire that these wires are wrapped around either there can be an air core or a solid core solenoid. So this is a solenoid, and so you got wires coming around, and then each one of those wires is creating a magnetic field. But let's look at this in a little bit of detail. So if we just consider one coil, it's basically a loop, right? And in that loop, current is flowing around it. Okay? And so if we think about that, let's look at the magnetic field right next to the wire. Well, right next to the wire, if we point our fingers in the direction, or our thumb in the direction of the wire, we can see that on this side of the wire, the magnetic field is coming out of the page towards us. And again, over here, it's coming out of the page towards us. So the whole thing on this loop, all of the magnetic fields on the inside of the loop are pointing out of the page towards us as long as the current is counterclockwise there. Now, if I stack another loop in front of that, that's going to add a magnetic field because they're just going to keep adding their magnetic field. There's going to be another loop there. It's going to add another set of magnetic field lines that are pointing in the same direction. And that's essentially what's going on here. We can see that this magnetic field line is being pushed this way, and then this one's here, and then this one's here, and then this one's here. And so however many loops there are, in this case there are n loops, that's going to determine, together with the current and the length of this solenoid, how strong the magnetic field is. And so we get this equation, B equals mu naught NIL, where N is the number of coils or loops of wire, I is the current in the wire, and L is the length of the solenoid, not the length of the wire, the length of the solenoid. And in fact, there's another right-hand rule here. You can use the right-hand rule for every current, but if you wrap your fingers in the direction of the current in the solenoid, then your thumb will point towards magnetic north if you're using your right hand. But you can do that with the other right hand rule too. You just, okay, so each one of these magnetic field lines adds up. And so what you can see is this solenoid actually creates a magnetic field that looks a heck of a lot like a bar magnet.